Alright, so in this particular video, we're given 100 grams of radon gas, 222, and it asks for A, B, C, D. So let's do it. Here's the graph of radon gas 222, and on the left side here it says activity in percent. So here's 100% is your original amount. Your original amount will always be referenced as 100%, but in this problem, it says that 100 gram of radon is how much you're given to start. So 100% is equivalent to 100 grams for this particular problem. And if it wasn't 100 grams, let's say if it was 500 grams, then 500 grams would represent your 100%, how much percent you have to start, okay? So in this particular graph, it says you start with 100% and then you go all the way to 40%. But part A asks us to find what is the half-life of radon 222. Well, half-life just tells you find out how much time it would go from the full amount to 50% of it, like 100% to 50%. So the graph here tells us the activity in percent. So this is 100%. The first split would go from 100% to 50%, right? Whatever the amount is, but the percentage just stays the same, okay? So this is 100%. I want to go down to the graph. I want to find 50% of whatever this amount is. It just happens to be the same number, which is 100 grams in this one. It doesn't have to be. So 50%, if I go all the way across, it intersects the graph here, this decay graph, at about 3.8. So I'm just going to put a dot. That's where the graph intersects, and then I'm just going to say that that is 50%, which is the first decay, and then that right there on the time axis is 3.8. Okay, so every little tick is 0.1 of a day, so that'd be 3.8. So the half-life time here is 3.8 days. So every 3.8 days, this particular 100 gram sample decays. All right, so we start with 100 gram. After one decay, it goes to 50 grams, which is about 3.8 days. Let's go ahead and do part B. Part B asks us to find how much is left after 17.1 days. So we're looking for n of t, okay? So n of t, by definition, this is one of the functions that you can use for half-life. It's the original amount, so your starting amount, divided by 2 raised to the time elapsed, divided by the half-life time. So keep that in mind. There are two different types of t here. T in the numerator is the amount of time that has gone by. T half-life is a constant for this particular problem. So T half-life we just found is every 3.8 days, okay? So we know everything already. We know the original amount is 100 grams in this particular problem because it said so. And then T is 17.1 days for part B because it wants us to find how much how much of this gas is left over after 17.1 days has gone by, okay? And then T half-life is 3.8 we found. So little plug and chug action here. And not, it's a 100 grams. T on the top is 17.1 because that's how much time has gone by. 3.8 is the half-life time. And then 2 here in the denominator is, raised to that power. Okay. So if you simplify the power, 17.1 divided by 3.8 is 4.5. And then all we have to do really is simplify 2 to the raised to the 4.5 or 4.5 power here. And that would be 22.627, and then the numerator stays the same. So now we have 100 divided by 22.627, and that'll give us 4.42 grams. And that is it for part B. Okay. Again, this is one of many functions or the many ways you can write half-life out. Part C. Part C asks us how much has decay after 38 days. So I do want to underline the phrasing here. It has decay. Unlike part B, asks for how much is left over. So after 38 days, this is your T here, okay, not T half. Again, 3 half-life is 3.8 days, so T here is just 38 days. So we're trying to find out how much has decays. For me to do that, I have to figure how much is left over, and then once I figure how much is left over, I can just simply subtract it from the original amount. So keep up here. So I want to find n of t, once again, and now it's given us 100. T here for this particular part is 38 days. You notice T half-life in the denominator of the exponent hasn't changed because we figured that out for every 3.8 days. It splits again and again and again, okay? So we simplify all this. 38 divided by 3.8 is 10, so it'll be 2 to the 10th power. And then if we raise 2 to the 10th power, we'll get 1,024. Numerator hasn't changed, which is your original amount, which is 100 grams. So if you take 100 divided by 1,024, you'll get an answer of 0.0977. But n of t is how much is still left over, okay? But the question didn't ask for how much is left over. It asked you how much has decay. So to figure out how much has decay, I would say use a common sense. And I would say, well, you started with a certain amount, right? You have a certain amount left over. So to figure out how much has decay, you just do a little subtraction. So here I said amount decay is equal to the starting amount, subtract how much is left over. Well, your starting amount in this case is 100, and then your remaining amount after 38 days is 0.0977. So just take the difference. So starting amount is 100, subtract how much you still have, which is 0.0977. That will tell you how much has decay or how much you've lost. All right. So other than that, the amount that has decay for this particular problem after 38 days is 99.9 grams, which is majority of the mass given or the sample here. Okay. All right. Let's do part D. Part D asks us to find how many days it would take for the sample to go 1/30th or 32nd, 32th, however you want to say this. To do that, all we have to do is to really set up the same function again, but in this case, I'm just going to go ahead and go with this particular function for half-life. So n of t here is n naught times e to the negative kt here, where k is your decay rate. Okay. All right, so you notice here on the left side, n of t, instead of saying n of t, the problem tells me that it's 1/32 of the original amount. So that's where the fraction is. So it'd be 1/32 of the original amount. The original amount can be expressed as n naught. On the right side, all I did here was I substitute out for k. So instead of saying k is 0.693 divided by the half-life time. And the half-life time in this case would be 3.8 days. And then t on the outside of k here, or to the right of k here, just gets carried down. And this t here is the amount of time that has gone by, which is what we're trying to find. Okay. So as you can see, on both sides here, we have n original, or n naught, and n naught, which is the original amount. So I'm just going to go ahead and cancel these terms out. So the left side really reduces down to just 1/32. The right side, I just carry down what I have not been simplified yet. So to do this, I'm just going to go ahead and get rid of e by ln on both sides. So it'll be ln of 1/32. And on the right side, to get rid of e, I need to get rid of e in order to bring the t in the exponent down, because I'm trying to find t. So the opposite of e would just be ln. So getting rid of e is just ln both sides. So the ln on the left side stays, but ln on the right side cancels with e. So really, you're just bringing down this exponent, which I haven't done anything. Okay. So on the right side now, instead of this term being an exponent, it is now as part of the function, the main function here, which is 0.693 divided by 3.8 days and then times t. Ultimately, we're trying to find what t is, because the question asks us how many days would it take, right, for this particular sample to just have 1/32th left. All right. So to simplify this, 0.693 divided by 3.8 gives us 0.1824 times t, because t's are unknown here. ln of 1/32 will give us negative 3.466. Well, to find t, divide both sides by the coefficient in the front, which is negative 0.1824. So if I do that correctly, I'll get about 19 days. Okay, so that's one strategy to do it. That is to use ln to get rid of e. The other way to do it is using the same function that I've used a few times already. Here, we need to find t. We were given n of t, we're given n naught, and then we know the half-life time already, which is from part A. The graph itself is 3.8 days. So I'm just going to go ahead and plug in similar strategy here. So instead of saying n of t, I can say this as 1/32 of the original amount, because that's what the problem says. It gives us to us in a fraction, right? On the right side, n of the original amount, n naught in the numerator stays the same, right? T stays the same because that's what I'm trying to find. And then t half-life, I just plug in 3.8 days. So if we do this, n naught simplifies because it appears on both sides. And then here, I'm just going to do a little switcheroo. In order to get t so that it's solvable, I need to move this whole entire denominator on the right side to the top left. And I need to move 1/32 to the bottom right. But as you can see, this is 1 divided by 1/32. So anytime in math, if you divide by a fraction, you would multiply by the reciprocal. So on the right side, the reciprocal of 1/32 would just be 32/1. So 1 times 32 is 32, divided by 1 is just 32. On the left side, I haven't done anything yet. Okay, but I do want to point out here that t here is in the exponent. So to get t down, so where you can solve for it as a variable, you have to log both sides. Okay, the only way to bring t down is to log both sides. So we're going to log 2. That brings the exponent down. So you notice how it's written here. It's on the same main function now. Okay, and then you got to log the right side as well. Well, here I can just do log of 2, divide by 3.8, and then I can divide that by log of 32. So if you want to do this, if you do log of 32, you'll get 1.505, and then if you do log of 2 divided by 3.8, that'll give you a coefficient of 0.0792, and then you need to bring it to the bottom right. Okay, so hopefully your algebra is good that you're keeping up here. Other than that, if you punches in 1.505 divided by 0.0792, that'll also give you 19 days. As you can see, the answer is the same regardless of whichever starting point you want to start with. Okay, hopefully you know when to use ln and when to use log, and hopefully your algebra is good enough to finish it properly. All right, stay nerdy, don't be whack.